kick off our research seminar series with Dr. Katie Rich, who is from the American Institute for Research, and also Carla Strickland, who's from UChicago STEM Education Department. In her role as a senior researcher, Katie works on, I'm just going to make sure I've got all the details right. She works on a variety of projects related to this to K-5, so again these younger learners, mathematics and computer science education. She's passionate about supporting teachers and helping all students to feel empowered as capable mathematicians, computer scientists and problem solvers. Carla works as a digital development manager and is an expert in digital enhanced STEM curricula. That's STEM curricular teaching and learning. And she brings a passion for equitable, high quality instruction to her work in education. And in our seminar today, I'm very excited about the seminar today. They're going to discuss the process for developing instructional approaches to the teaching of computer science topic of variables, and how they've coordinated this research about variables with the reality of classroom activity in the classroom context. And I think that's really important for us all to kind of get to grips with. So
thank you so much, Jane, and all of you. Good morning, good afternoon, or good evening, depending on where you are in the world. We're really delighted to be here. And I'm gonna, since we got such a wonderful introduction, you know a bit about me and Carla, and I'm gonna dive right in to the presentation.
Fantastic.
So the work we're talking about today comes from the LTEC project. So that's the name of the project that started this work. And LTEC stands for Learning Trajectories for Everyday Computing. So this work started as a grant from the National Science Foundation. That's what NSF means, a federal funder in the United States, under a program they had called STEM plus C, which stood for STEM plus computing. So it was when computing education was becoming its own research discipline, really up and coming. They had a specific program to think about integration of computing with other topics. And so we at UChicago STEM Education, which should be clear is where I worked at the time, although my professional home has changed since then, we're interested, we have a curriculum there called Everyday Mathematics, which is pretty widely used in the United States. It's a kindergarten through 6th grade, which is, we call it elementary. Primary age is another term for it. It's roughly ages 5 to 10, 5 to 11. That we're talking about there. And we were interested in the idea of integrating some computing content into our everyday mathematics curriculum. But as we looked at the body of research, one thing that really struck us, was that there was a lot of research out there of great researchers doing work with how kids this young would think about computing, the kind of topics they would use. There was development of languages and block-based programming that would support that. But we were really struck by the fact that almost all students in the research studies were being treated as beginner programmers, beginner computers, which means, which made sense to us because we were at that point, and still are to this day, where we can't really assume that kids, especially in primary school, are coming into school with any experience in computer science. But as curriculum developers, Carla and I and the rest of our team always took the long view when we were thinking about developing instruction. We were always interested in development of instruction across a grade level and even across grade levels. So we were really interested in this idea of how can we develop coherent instruction across a school year or multiple school years. And we found that individual studies weren't helping us much with that. So we kind of embarked on this project that we called LTEC, where we started with a literature review and followed it up with some dedicated activity development that was trying to answer these questions. So first, what big ideas in computer science should be addressed in K-5 curricula or primary school? Again, about ages 5 to 10. How can we express them in ways that make sense to K-5 students and teachers? This was really important to us too. We had a lot of experience with everyday math of translating mathematics education research into instructional materials that would make sense and be practical for kids and teachers. And especially, how should those activities and the instruction grow across time? So we conceptualized this work. I like this graphic I have on the screen here because we really conceptualized the project as trying to bring things into focus that we knew, but the pieces hadn't quite been put together yet. Sometimes the language we used was we were articulating the unarticulated. So we were trying to look across studies and put ideas together into a skeleton, at least, for some coherent learning trajectories across time in primary school. So we used learning trajectories as a theoretical basis of our work, which suited us because at least the definition that we took from the mathematics education work and learning trajectories was that they have three parts. There's an overall goal or idea you're trying to develop in students, kind of the aim of the learning trajectory. There's a developmental progression that helps kids move toward that goal or that understanding. And then there's also the instructional activities that facilitate movement along that progression. So we really conceptualize this work as using a literature review to kind of define what those goals would be and give us some ideas of the developmental progression, and then using activity development to help us think about that third part and really develop the trajectory into something that was going to work in practice in a particular context. Because we all know kids, different contexts, different backgrounds, need different things in instruction. So we really like the idea of learning trajectories and the development of learning trajectories, both involving what we considered our forte at UChicago STEM Education, which was curriculum development, and being flexible and responsive to what kids and teachers need. So that was kind of the overall aim of the work. It started with, let me pause for a second. Just to be clear, we're going to be talking about variables trajectory today, mostly. But we just want to make clear we do have 6 trajectories altogether that came out of this work. So sequence, repetition, and conditionals, decomposition, debugging, and then this one about variables. The first 5 have papers associated with them that have a graphic depiction in them, or I should say all 6 do. All 6 have a graphic depiction like the one you see on the screen in some papers you can look up and we can share if you would like. But we also have a website that has visualizations of the trajectories where you can really dig down and see what the research evidence was that we based them on. But so we're going to unpack a little more about the variables trajectory today, though. That is sort of our most theoretically developed one because it was the last one we did and we were learning as we were going about how to do this. Just to give an overview of the methods, we're going to spend the most time on the activity development pieces because we thought that was most of interest to this audience. But just to give you a sense of how we started this work is we did a literature review, but it was a little bit different than a traditional literature review because we weren't just summarizing studies and trying to compile them into a paper. We specifically started our work by extracting learning goals from the papers. So we were really looking at, in each of these papers, what were the things that kids either showed evidence of learning or the researchers were saying they should be learning, we want them to learn. And we really extracted those individually as statements of learning goals. And through that work, we ended up with a collection of over 570 learning goals that had been addressed in research over a period of 10 years. Just to be clear, we did 2006 to 2016, I believe was our time period. So we had a collection of learning goals, but again, our goal was to organize them into some kind of coherence that could guide developmental trajectories. So we had to start a little smaller than doing all 571 at once. So we tried to identify particular topics or that big picture end goal for individual trajectories, and we did that through keyword searches. So once we knew we wanted to, for example, do a trajectory about variables, we had keyword searches on the collection of learning goals for things like variable, string, value, et cetera. Those terms vary depending on which trajectory we were doing. And what we ended up with was what we called a cluster of learning goals focused on a particular topic. And then the real work began in some sense because the next part was 2 kinds of synthesis work that we did that took a lot of collaboration and mutual expertise from our team members. The first kind of synthesis we did was trying to collect the different ideas and we call them fact and skill goals. So what are the ideas, the topics, the facts, the things we want kids to be able to do related to variables in primary school? So basically that happened by we had individual team members with different kinds of expertise. So curriculum development, math education, computer science education, just computer science as a discipline, did independent sorts of that cluster of variables learning goals. And then we collaboratively came together and said, what groups did you come up with, and came to a synthesis on what are these collections that form a coherent idea we can articulate as what we call the consensus goal. We use that term to mean there was more than one paper that we're saying had consensus on a learning goal. So just to give you a brief example of what that looked like, these were 5 learning goals from the variables cluster that ended up together in a consensus goal about initialization. So you see they're all related, but they have sort of different flavors. So learn the importance of initialization, abstract the need for initialization, attend to initialization, not clear exactly what attend means, initialize the properties of sprite, so actually do it. So we ended up collecting those together because they were related about initialization, and we didn't feel like we had enough consensus about which flavor of those things to articulate it into one goal, just about, say, abstracting the need. So we ended up with consensus goals about variables that were about things like initialization, types, updating, things like that. So this collection was really useful, and it gave us sort of the grist of what we wanted, what were the basic things we wanted to teach kids in our instructional materials, but it didn't help so much, especially in the case of variables, with the progression, because it wasn't always clear. There wasn't always a hierarchical ordering of the different skills. Sometimes there was more information about that for things like sequence and repetition, just because there's been more work done. But for variables, because there hadn't been as much done, at least at the time, in primary school, we had less information about that. So the second kind of synthesis was really important to our work. And that was synthesis into levels of thinking about variables. So these are different than fact and skill goals, in the sense that we're not thinking about what we want kids to be able to do or know, but rather how we want them to think about variables. So they, in the research on mathematics learning trajectories, they talk about this as a level of thinking being defined by the objects, the cognitive objects that a student has, and the operations they can do on them. So my favorite example to talk about for that is when kids are just developing their understanding of number. So very young children, like preschool age, will typically develop the count sequence first. They can count 1, 2, 3, 4, but they don't necessarily have a quantity associated with that right away. So they have a cognitive object that we would call a number. They have a thing they can think about with this word label, but they can't do a lot of mathematical operations on it because there's no quantity associated with it yet. But later on, when they move to another level of thinking, they start to associate quantities with 2 and 3, and then that operation of adding makes a lot more sense. They've moved to a new level of thinking about number. So trying to translate that into what levels of thinking that kids might have about something like variables was our task at this stage. So what we did was go back to the literature base and really try to unpack the learning context that was associated with each of these learning goals we had extracted. So we really went back and said, what activities were kids doing, and what did that suggest about the levels of thinking they were developing? So how were they asked to think about variables? What mental objects did they consider? And what operations did they carry out on the objects? So just as a brief example, which I know doesn't impact it entirely, but one annotation we made was this particular learning context said, there's a quiz question related to variables that asks how can you keep track, of how many times the bat has been hit by a banana? And we said, okay, if kids are meaningfully answered that as a variable is how you keep track of this, then they have an object for thinking, a cognitive object for thinking about data, that how many times is a thing they can think about. And they also have the idea of keeping track, a storage space. That's another object. And they have this operation of putting the data into the storage space. So that's the kind of thinking and extraction we were doing, again, independently and then collaboratively, to come up with levels of thinking. Just based on the literature review, this is how far we got on levels of thinking. So we had 4 to start with. I'm not going to unpack them all completely because we're going to talk about it more in the context of the activity development. It's going to make more sense then. But just to give you a sense, we're starting with data user, which meant kids have that cognitive object for data. So what I was just talking about, that they know 3 has meaning as a quantity, for example. They can think about data and they can manipulate it. They move on to data storer when they have that storage space I was just talking about. And then they make this shift to being a programmer and think about variables as a construct in programming. And then eventually they're able to create variables with new objects associated with that. But these are easier to understand in context and also changed a little bit based on our activity development. So that's as much as I'm going to say just right now. So with the collection and fact and skill goals and the levels of thinking, we're getting closer, but we're still not at a trajectory. because even among the levels of thinking, it left a lot of space for how do we actually facilitate that transition from one level to another. And it left a lot of questions about how these facts and skills like updating or types or initialization, how does that fit into that picture of moving along that trajectory? So our tool for thinking about that process, bringing those two things together and also bringing in all this thinking about context and student needs was activity development. So as we were developing activities to address variables, we were being attentive to fostering progression through those levels of thinking, but also thinking about how to bring in those facts and skills and lots of other stuff we were considering. Here's the classroom realities, right? We, in particular, were integrating computing into mathematics that was already taking up a lot of time in the school day, so we couldn't just take as much time as we wanted. That was one constraint. We had a particular age level, so we were working in 4th grade, which is about 9 or 10 years old. Instructional conditions, so what knowledge are kids bringing into the classroom? What knowledge are the teachers bringing into the classroom? What can we assume about that? And which programming environment are they going to use? In our case, we use Scratch, but things might change in terms of what it means for types or updating or all these other things based on what language you're using. So we had all these considerations that we were bringing together to create a specific trajectory for our context through activity development. So I'm going to turn it over to Carla in just a second to talk more about the individual activities, but just as a little preview, here's what our final trajectory will look like for our purpose of activity development. So you'll notice right away that there's actually 5 levels at the bottom instead of the 4 I showed you before. We'll talk a little bit about that. And then these jumps that you see identify both the bold text is those facts and skills we addressed through the activities we use to facilitate that step. And then the italics is the name of the activity or activities we use to facilitate that. So we're going to unpack not all of it. We don't have time to address all the activities, but Carla and I are going to walk you through one activity for each of these 3 transitions you see. But right, before we dive into that, Carla's going to give you a little background on the full curriculum and some of our other considerations.
For teaching variables, we ended up with 6 lessons that focused on them. Sorry, this is 5 here. The last one is a project which synthesizes everything. So we have 5 listed here. And these 5 are part of an entire sequence of lessons. There are 25 of them. On the far right, you'll see that they are numbered 15 of 25, 16 of 25, and so on and so forth. So you can have an idea of when they come. One of the reasons we wrote this collection of lessons, this 25 lessons, is that we wanted to test out the learning trajectories to see how they could be used to create coherent instruction across 2 school years. Those school years are referred to as 3rd and 4th grade in the United States. If you're international like me, and I grew up in the British Caribbean, so we say standard 3 and standard 4. You want to add 5.5 to the grade level, right? So students in 3rd grade enter at age 8 and are turning 9. Students in 4th grade enter at age 9 and are turning 10 during the school year. So there are about 13 lessons in 3rd grade and 12 lessons in 4th grade. And so you can see when we decided to tackle variables was later in the sequence, because we also did some work with those other trajectories that you saw. So we dealt with sequence and repetition and conditionals and so on. Right, so these lessons that we're going to look at today, we're going to look at robot boxes, which is an unplugged introduction to variables. We did this in math. You'll see in that second column, right after kids were talking about area and perimeter of rectangles. So we thought that would be a good place to put that in. And then the rest of the lessons come during the fractions work that kids do in 4th grade. And so you'll see those fractions context as we go on. Katie, I think that you can go to the next screen. I just want to talk a bit about language. We have said that we did integrated instruction. So we were integrating computer science or computational thinking into mathematics, which already dominates the school day, certainly in the United States. And so we did not have the luxury of saying we're only teaching computer science or coding. So when we give a term, we're only talking about it in this sense. When we use words like variable, when we use words like abstraction, when we use words like condition, we're not just dealing with natural language or common usage that students may bring in. We're also specifically using the word variable that may mean two different things in mathematics and computer science, and we're dealing with that in the same period. We're asking primary school teachers or elementary teachers to talk about variables and define variables for kids that in their minds, those meanings, the senses of the meanings need to be clear. And so we did a little bit of work thinking about these overlaps, the similarities and differences in discipline-specific definitions, and how that would impact and or affect students and teachers' learning and understanding of those terms. And we said, hey, this is integrated instruction. We cannot leave it up to teachers to figure it out and explain it to kids, right? We need to anticipate these factors and help students who are both novice learners and young learners to develop this academic language with nuance in this integrated setting. Katie, if you would advance the slides for me, please. So let's go right to talking about robot boxes, which is the first example. Advance a little bit more for me, Katie. Right. So in this activity, this is an unplugged introduction to variables. Now, this is 4th grade. So students have already seen X and Y, which are like the top 2 most popular variables, right? And they might think they know what a variable means. And the teachers definitely think they know what a variable means. And so we wanted to be careful with this introduction in a computer science context. So we started with a game and we didn't even say the word variable until the wrap up, which you see written up on the end. We just said, hey, we're going to do this game. You're going to pretend to be a robot. One person is going to pretend to be a robot. One person is going to be the calculator. One person is going to be the filler. You already know how to calculate the area and perimeter of a rectangle. And so this is going to come off as a game. Each role gets an instruction, a list of instructions, which is like a program, right? And you have to follow your instructions. So they first have to come up with, if you see in the middle here, and I'm like moving on my screen, but Katie is sharing, so you can't see. I'm circling the middle here, which is some boxes. There's 6 boxes. They are labeled message, length, width, my action, measure, and answer. And kids can use Post-its or index cards to choose something to put in each box, right? And so the filler is responsible for that. And so the filler is like, oh, what's a message? Oh, what's an action? They, of course, do a demonstration. Here we have filled out, you see that the text, perhaps you see that the text is in magenta. This is an example that we created for teachers to show how an instance of the game might be played. So here the message is, I am a robot and I love rectangles. The length is 3. The width is 4. My action is jump. The measure is area and the answer is 12. Once those values are in these boxes, then the robot is able to execute or run their program, go through their list of instructions. And so the robot will say, I am a robot and I love rectangles. And then they move 3 steps. They say, I am 3 units long, so on and so forth. The kids love this. They do love to do a robot voice. The actions were much less tame than jump. Okay, we had kids dabbing because it was 2016. We had kids spinning, and so they had a really nice time. In effect, in mathematics, pacing out the perimeter of a rectangle. And then the calculator is responsible for taking those same 2 values, length and width, and either calculating the area or calculating the perimeter based on what is in the measure box. So you can see all the instructions for this, but they have a blast playing this game. And then in the wrap up, we ask teachers to say, explain to the class that measure, length, width, my action, measure, and answer are called variables. A variable holds a value. That value can change. They know this because they played the game at least 3 times and they physically changed the values in each box. They took the old post-it off, they put the new post-it on, and so on and so forth. We used an actual box. We had that physical laying of a card for assigning values to each variable. To clear out those values, they removed them. We talked about different variable types here. We asked kids to think about it, even though it was implied there. We said, what would happen if you take what's in message and put it in width? Can you add 3 to the sentence, I am a robot and I love rectangles? Does that help you find the area? So we get to talk about this. This is their unplugged introduction to variables in a computer science context. So if you now, Katie, go to the view of the variables trajectory, you'll see here that this lesson focused on this notion, students being data users and learning about activity types. It's the first thing in the trajectory. That first motion, which is understanding what a variable is, understanding that you can use it to store data, understanding that it has different types. That's our activity that we use to illustrate there. Casey?
Yeah, so we were really like going back to the levels of thinking and the way we're trying to progress along there. So they're moving from what we call data user. So we're assuming that kids in 4th grade, which again is plus 5.5, 9 or 10 years old, are coming in with the ability to think about data, especially numbers, and manipulate it, right? So we think they have this data user level, but we're trying to move them here to what we call the data store level, which is adding a new object to think about, which is a variable, which we're representing concretely in this case, in this introduction, as the box on paper, and that operation of storing and removing data from a box, right? A variable storage space. So we're having them physically see and physically execute these cognitive actions we're trying to build. You'll see when we move to the next one that instead we make this next transition, which let me just go there, from what we call data store to variable interpreter, because they're making a very important change in perspective here. That's why we have so much stuff above this transition, is that they not only are doing that action and having those actions during that time in that activity, kids are the computer in a sense. They are the filler, they are the robot, they're doing the calculation. But when we're helping kids to learn how to program, they're really shifting perspective, and it's like, now I am the agent that's telling the computer to do those things. So they still need to be able to do those operations in their head, but there's a new change of perspective and a new perspective on the objects where they are telling someone else to do these things, or, to the extent that we think of computers as being personified in something we're doing. So to facilitate that transition, we were really mindful of moving from kids physically doing the action to having them tell the computer to do that action. And Carla will give you an example of what that looked like.
Fantastic. So we're jumping in here on Ambling Animals. You will see several alliterations. I was going through a phase at that time. So who doesn't love a good alliteration? Ambling Animals. And the mathematics that we decided to pin this activity with, children knew about fractions, mostly as collections of objects. But then that understanding of fractions has to move to a location on a number line, a distance from 0. So students need to be able to understand a fraction as a location on a number line. And then once they understand that, that helps them compare fractions in a different way. One of the early strategies that children use, that they are taught to compare fractions on a number line, is you have a fraction on a number line, you have another fraction on a number line, and you line them up vertically, and you use the straight edge to look to see which one is further to the right. That one is going to be the larger fraction. So in this case, we have a crab on that one on top here on the A crab is labeled. And then on the bottom, we have a frog. And the frog, if these two number lines are aligned, the frog is further to the left. So students might say the crab's fraction is greater than the frog's fraction. And that's what they would do in class. We actually have lessons in everyday mathematics where kids are actually drawing the number line, locating the fraction on the number line, doing it again, lining them up. This takes forever for little kids. They spend a lot of time stressing themselves out over the number line representation rather than the fraction comparison. And so we're teaching computer science. We did not want to just do unplugged activities. We wanted to do use programming environments. So we use Scratch, which is very popular with the primary school set. And so we decided to write a program to automate this number line representation within the context of comparing fractions. And so if you go to the next slide, please, Katie, you see here, this is a screenshot of our Scratch activity. If you want to go and check it out yourself, you're welcome to do so. You will be able to find the link in the list of lessons that I provided to you earlier, right? And so how this goes is that they get on there, they can, when they hit the green flag, the program randomly animates, the crab moves back and forth and then settles on one spot. The frog does the same thing. The program asks them which animal represents the greater fraction, and they can click guess to type in which one they think it is. If you move from the previous screen with the two number lines to this screen and you try to use the same strategy of vertically aligning the number lines and just choosing the one that's further to the right, you might say that the frog is further to the right, and so the frog represents a greater fraction. And children might say that too, but that's not correct because these two number lines are not vertically aligned. If we did that mental shift in our minds, we would say, oh, obviously the frog is further to the left and it's the crab that's further to the right. We cannot assume this of young children learning mathematics at this time, right? So they cannot drag the number lines. So then what do they use to determine the greater fraction? Well, we have benchmark fractions. So that's the next strategy that they progress to in mathematics class. Is it closer to 0? Is it closer to 1/2? Is it closer to 1? Those are the three first benchmark fractions that we teach. And so that's the strategy that we hope kids will apply when trying to determine the greater fraction. This is mathematics. We're not even getting into the computer science yet, right? So we just have them play this a few times. It randomly generates different problems. And then we're like, hey, put your guess in. Which fraction do you think is greater every time the program runs? After we do that, we're then able to say, hey, what if you were the programmer and you're able to change this program to say maybe whether the guess that somebody puts in is correct. And so, Katie, if you would go to the next screen, this is a link to the Scratch project. We actually have real children who use these Scratch projects. So we were able to pull one of those remixes and pull some kid code. And that's the code on the right, the remixed code from a student. The starting code that we gave them is on the left. You are seeing here the ask block, which is in blue. It says ask the question and wait. Whenever you use an ask block, the answer that the user gives, the input, is stored in a variable. That variable is represented by this oblong blue block there that says answer. If you know a little bit about Scratch, I apologize. I am not speaking down to you. I'm just trying to be very clear. Right? So we give them this code. You'll see also that there is there are two if blocks then, because we're also doing conditionals at the same time. And the student remix this code. Right now it's set so that if the answer that the user gives is crab, then the program will say snap, snap. If the answer that the user gives is frog, then the program will say ribbit, ribbit. But this has nothing to do with what the correct answer is. It's always going to say snap, snap when you put in crab. It's always going to say ribbit, ribbit if you put in frog, which is nice, but that's not telling me anything about whether my answer is correct. So we asked students, if you could change this code to give a particular answer, to tell whether a particular answer is correct, how would you change it? And this student changed the code as following. They were able to tell that the greater animal variable held the actual answer to the problem, the correct answer to the problem. And so they set up a comparison between the user input, which is in that blue oblong block, and the greater animal variable, which is in this orange greater animal block. And they said, if it's not equal, then say you are incorrect. Click the green flag to try another one. If it is equal, then say you are correct. This is actual student work. We did not make up this child. I did not compel the child that lives in my house to create this. They actually did this. And so you see here that we moved students during the course of the lesson from the perspective of the user to the programmer and back and forth, so that they are using their mathematics context to learn about this concept of variables and how you use them in a program. You will see if you go into the lesson materials that we actually use the tip and see strategy for this. And as it turns out, the next talk in this sequence is from Dr. Jean Salak, who is going to talk about the tip and see strategy for understanding Scratch programs. And so if you want to hear more about that strategy, you can hear it next time. I'm just giving a little free publicity for the next talk. But we did use that tip and see strategy in our student materials and teacher materials. Katie?
Yeah, so before we move on to this next activity, I want to make two just kind of points on here that I think are important to emphasize. One is when Carla was talking about this shift in the number line, how we shifted the number line so kids couldn't just line up the fractions in order to compare them. That was actually like a really big point of discussion when we were developing this, because we were also thinking about how we're offloading that work of creating the number line and figuring out where the fraction goes to the computer. And we talk to kids about that and say, that's one of the things computers are good for doing these tasks that we can automate. But we wanted to also not give them the idea that the computer does all the work for me and all I need to do is line up the use my straight edge to see which one's further to the right. So we're trying to promote this idea that there is still sense making going on when you're using a computer or a calculator. And we contrived that a little bit here by shifting the number line. And we'll talk a little bit more about that benefits and cost of those contrived contexts. But that is one of the reasons we emphasize this. And I just thought it was an important point to bring up, because it's another one of those things about classroom realities and research, right? Is that, when kids are just using a computer any way they want, they probably could use that contrived context and then make it really easy for them to compare fractions. But because we were also trying to serve mathematics learning goals, we did that little bit of contrivance and also use the opportunity to talk about sense making when you're programming.
It's an important point for the learning trajectory and where you apply it, right? If students have been drawing number lines for 6 years, by the time you're going to talk about this, then it's trivial for them to do that mental shift, to create the number line representation themselves and do that mental shift to compare. But if you are introducing this at the time when students are also learning about fractions on the number line for the first time, and also when it is difficult for them to create this representation, then there's a lot of cognitive load to the creation of the representation. And so being really strategic, and I don't, I'm preaching to the choir here because we've got a bunch of elementary and primary school level educators here. You're not going to look at me and be like, this is such a trivial problem. Why do you think this is hard for kids? You know why, right? They're not just novice learners, they're young learners. And so that played a lot into our considerations. We were really thinking about teachers and all of the things that teachers are trying to teach children at a particular time. And so we were very intentional about where we placed these activities. Katie, you can go on to the next one.
And then, yeah, just one more quick point about this leap is that you'll see we actually have 3 activities facilitating this. And we wanted to emphasize that because we do think this transition to thinking like the computer, to thinking like a programmer is non-trivial. And you need to go like facilitate that kind of shift many times. So that's, I just wanted to make that point really quick because I know we're close on time and we've got one more to go. But we do want to emphasize that when we think about learning trajectories, we don't necessarily think about just a linear progression that we check the box and we move along. They're really tools for thinking about how to help kids make transitions. And you may need to kind of step back just as a thinking tool or just because kids haven't fully made the transition. It's a useful tool to think about even within an activity about where you want to start within the trajectory, even though you're also doing the long-term development as well. So really, we'll try to be quick on this last one because I know we're tight on time, but so now we are moving along to the last transition, which this used to be just one level of thinking. When we showed the ones from the literature, it was just called variable user. But what we realized when we were developing and going from variable user to variable creator is there's actually a lot to be coordinated. And Carla was making the point earlier that we're not just dealing with novice learners, where maybe if you're an undergraduate programmer and you're new to programming, and you know, you're switching from just understanding what a variable is to then implementing one from scratch, no pun intended. Maybe you can coordinate a lot of those things at once, but we found that for young kids, we really had to think about some stepping stones in there. So Carla will show you what that looked like in activities.
All right, quick. So here we go. On the left, we have a screenshot from the Scratch program. By this time, this is closer to the end of the school year, they have seen fractions in their symbolic form. They have seen fractions. They've used the fraction circle manipulative, which you're seeing there. They have used fractions on a number line, and they are now learning strategies for adding fractions together. I know y'all remember learning about fractions. The first kind of fraction you add is fractions with like denominators or same denominators. And then later you learn how to add fractions with unlike denominators. And so here they're learning how to add fractions with like denominators. We created a program that coordinates all the different representations that they have used, right? And then it animates that little, what it is, a duck, a goose, maybe it's a duck. This little duck flies across and does 2 hops on this number line. It's hopping over that pond, which is that blue blob down there. You know, it works. And it adds the 2 fractions together. If you add the 2 fractions, the fraction that you land on is going to be the sum of the 2 of them. Kids get it. They're into it. They talk smack about how the duck looks. That's part of the fun of it. The code is here. It says when you click the green flag for setup the program, it says divide the number line into 8 parts and then move 5 eighths and move 2 eighths, right? And so that's the initial program. We have kids run it. They are like, cool, cool, cool. We say change it. Do it with 6ths now. Give me 2 jumps with 6. Do it with 11ths. Do it with 3rds. They get really sick of us because they have to change the denominator every single time, and it appears 3 times in the program. This is how we contrive an efficiency argument. Wouldn't it be nice, kids, if you didn't have to change the denominator all those times? Wouldn't it be great if you only had to change it once? This is a great place to use variables, right? And so, you know, we're selling it. They're kind of buying it. And so we try to do this. And so we introduced that denominator block there. You're seeing it on the right-hand side. But then we were like, wait a second, we have to initialize the value of the denominator. We need to not just talk to kids about efficiency. We're going to need to talk to kids about initializing a variable and so on and so forth. This is what motivated that split that Katie was just talking about. We were in the midst of writing the program to make this efficiency argument. And then we said, there is too much here for kids to, you know, to deal with in 45 minutes. They think about fractions, they thinking about the duck, they're thinking about the denominator and the numerator and all that stuff. So we split that. So this is our activity that we did here. We're out of time, so we'll move on to the next slide. But again, You're going to get to talk about us in the breakout rooms and come back and ask us questions. And you have the link to all of these lessons. Katie, if you would go to the next slide, please. We want to talk a little bit about limitations. Katie mentioned this earlier, right? We were working within the US school system. This was, you know, we did a literature review on academic articles, all of them written in English, most of them about children in the American school system. And this was in the years 2014 or 2015 to 2016. It seems like a lifetime ago now. But, you know, this is when we did the work to get all of those learning goals. So we want to be humble and open with you about when we did this work. And we were assembling these learning trajectories that could live beyond the, you know, the actual time that we were doing the work and the papers that we had to consider. But there are more learning goals out there now as people do more computer science. People like you are doing more computer science with your students. So that's our limitation slide. We have a takeaway slide that I'll let Katie say.
Yeah, so these were just kind of the big things we hope you take away from all these details we got through. We really found we loved the levels of thinking as a basis for instruction because it allowed us to think about thinking and not just the questions we want students to be able to answer at the end. And we really love the flexibility of bringing in some of those facts and skills about variables in different ways according to our context. As we mentioned, we think there's a lot to unpack and maybe more research to be done about those variable user and variable creator levels and what levels of thinking are appropriate, especially for primary school kids to facilitate that transition along using variables. And again, young learners are not the same kind of novice learners as, say, undergraduate learners. And that really played into our work a lot. And we think that's worth thinking about in future research. From the practical standpoint, research to practice, you know, we talked about the benefits and costs of contriving scenarios for kids. But we did find that working with elementary teachers, which at least in the United States are often generalists, are teaching all subjects to a classroom of kids, were very flexible and predisposed to integrating computing into math. So that was really useful. And then the issues of shared language also had benefits and drawbacks because it gave us something to draw on in terms of knowledge they were bringing to the classroom, but also introduced some nuances that were difficult to address. So with that, we apologize for going over time. We just love talking about this work and we really hope you enjoyed it and can't wait to hear your questions after you have time to talk.
So I've got to say thank you, huge thanks to Carla and to Katie, and also to our facilitators. We've tried facilitators helping out, so thank you there. Can we give everyone a big round of applause? Told you before about Jean Selak is going to be coming along and talking about Tip and See, which is one of my favorite instructional kind of sequences, and that's just brilliant. So we look forward to seeing you at the next one. Bye-bye and have a lovely evening.
Thank you so much, everyone. It was delightful.
Thank you. I appreciate y'all so much.
Bye. Thank you.
Thank you.
Brilliant questions. Thank you.